The universe's largest structures are not what you think. We look up and see galaxies, swirling clusters, and brilliant superclusters, yet these are merely the dense knots in a far grander tapestry. The true titans of the cosmos are the immense, nearly empty spaces between everything else. They are called cosmic voids, and they dominate the fabric of reality. Understanding these vast nothings is the key to unlocking the deepest secrets of cosmic evolution, the force of dark energy, and our own fragile place within the whole. By the end, you will see the entire history of the universe, from its fiery birth to its distant future, through the lens of its growing emptiness. How did nothing become the most important something in the cosmos? And what does their silent expansion mean for everything else? What does it feel like to live in the shadow of such profound emptiness? This grand tapestry has a name, the cosmic web. Picture a sponge, a vast cosmic sponge, or the shimmering structure left by soap bubbles in a sink. The solid parts of the sponge, the thin walls of the bubbles, those are the filaments and dense knots where galaxies gather. But the holes in the sponge, the empty spaces inside the bubbles, they are not just background. They are the primary feature, immense volumes of near-nothingness that define the shape of everything else. For most of modern astronomy, our focus was understandably on the bright stuff. We mapped the great clusters, the sprawling superclusters, tracing the dense threads that connected them. The empty spaces were just the blank canvas, the negative space in the painting. But what if we had it backwards? What if the voids are not the background, but the very architecture itself? They are the complementary and dominant component of the cosmic web. To understand the story of the universe, we cannot just study where the matter is. We must understand why it is not somewhere else. The formation story of these voids is not a side plot. It is the central narrative of how our universe grew up and why it looks the way it does today. But what exactly is a void? We must move beyond the simple idea of an empty hole. A cosmic void is not a perfect vacuum. It is a region of space where the density of galaxies, of normal matter, is dramatically lower than the cosmic average. Picture a map of a continent at night, showing city lights. The superclusters are the blazing, dense metropolitan areas. The filaments are the highways and towns connecting them. A void is the vast, dark countryside, a sprawling territory where you might find only a few isolated farmhouses, their lights barely visible from one another. These lonely galaxies within a void are often older, quieter, and less active than their cousins in the dense clusters. They are the cosmic hermits, and while these visible galaxies are scarce, the voids are not truly empty. They are filled, or rather underfilled, with the mysterious dark matter that permeates all of space, just in a far more diffuse state. The scale is almost impossible to grasp. A typical void can span 100 to 500 million light-years across. To put that into perspective, our entire local group of galaxies, including Andromeda and the Milky Way, is about 10 million light-years wide. The immense Virgo supercluster we are part of is roughly 110 million light-years across. A single void can swallow several superclusters whole. This staggering scale is why voids are called the largest structures. They are not just random empty spots. They are coherent, bounded volumes, immense bubbles of underdensity with recognizable walls and boundaries, carved into the very fabric of the cosmos. They are the dominant architectural feature of our universe. The story of these immense empty spaces begins with a universe that was anything but empty. In its first fleeting moments, our cosmos was a searing, dense sea of energy, almost perfectly smooth. The temperature and density from one point to the next were virtually identical, a featureless, brilliant fog. Yet perfection is unstable, and within that primordial uniformity, the future was already written. The seeds for every galaxy, every filament, and every titanic void were planted by the faintest of whispers, quantum fluctuations in the fabric of space-time itself. These random, microscopic ripples created the very first differences, regions that were ever so slightly denser or ever so slightly more rarefied than their surroundings. They were the universe's first imperfections, and they would shape everything to come. We can still see the imprint of these seeds today, frozen in time. It is called the cosmic microwave background, the ancient afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. This faint microwave light is not perfectly uniform. It shows a mottled pattern of tiny temperature variations, cooler spots and warmer spots. Those cooler spots correspond directly to regions that were slightly underdense, where matter was a tiny fraction more spread out. This is a profound realization. The blueprint for the largest structures in the universe, the voids, is right there in the oldest light we can see. They began not as empty holes, but as subtle dips in the density of the cosmos, gentle valleys in a nearly flat landscape. For a long time, cosmology focused on the overdense regions, the hills that would collapse under gravity to become galaxies and clusters. But the underdense regions, the valleys, are just as critical to the narrative. They are not merely the absence of something, they are active participants, expanding faster than the universe itself, pushing matter outwards and defining the boundaries of the web. The fate of the cosmos was a contest between these two primordial seeds, the hills of matter pulling inwards and the valleys of emptiness pushing outwards. The contest between those hills and valleys was decided by a single, universal force, but one that played two very different roles. Gravity is the sculptor of the cosmos, but its work is not always about pulling things together. On the grandest scales, gravity's behavior becomes counterintuitive, and it is this dual nature that carved the cosmic web into its final form. In the overdense regions, the story is familiar. A slight clump of matter exerts a slightly stronger gravitational pull, attracting more matter from its surroundings. This creates a denser clump, which pulls even harder in a runaway process of cosmic construction. This is how the seeds became galaxies, and galaxies gathered into clusters and superclusters. Gravity built the bright knots of the universe. But in the underdense regions, the valleys of our early cosmos, gravity performed the opposite act. Here, where matter was already more spread out, the gravitational pull was weaker. The stronger pull came from the denser walls and filaments surrounding the valley. So instead of pulling matter inward, gravity began to pull the sparse matter in the valley outward, toward the denser regions on its edges. Think of a shallow depression on a hillside during a rainstorm. Water does not collect in the depression, it drains out, flowing toward the deeper channels around it. This is the fate of a cosmic void. This process has a formal name, void evacuation. Over billions of years, gravity systematically emptied these regions, pulling galaxies and gas out of the interior and depositing them onto the growing walls of the cosmic sponge. The void did not just stay empty, it became profoundly emptier. Gravity was not merely allowing emptiness to exist, it was actively creating it, amplifying the initial whisper of an underdensity into a thunderous shout of nothingness. So while gravity was busy constructing the great cities of the universe in the overdense regions, it was simultaneously and ruthlessly depopulating the countryside. It amplified both the dense and the empty, creating the stark contrast we see today. The cosmic web is not a static structure, it is a dynamic record of this great sorting, a fossil of gravity's twin ambitions. This process of void evacuation is not a gentle drift, it is a relentless cosmic current. As the universe expanded and evolved, the sparse matter within a void found itself caught in a gravitational tug-of-war it could not win. The pull from the denser, matter-rich walls and filaments surrounding the void is far stronger than the feeble attraction of the few lonely galaxies inside it. So, over billions of years, a great migration began. Galaxies, gas clouds, and dark matter are steadily pulled outward, streaming from the void's interior toward its boundaries. Think of a broad, shallow valley after a heavy rain. The water does not pool in the center. It flows down the gentle slopes, draining into the deeper riverbeds and streams that surround it. The valley itself becomes drier, while the channels at its edges grow deeper and more defined. A cosmic void operates on the same principle, but with gravity as the rain and the flow of galaxies as the water. This outward migration is the core growth mechanism for these vast structures. A void does not simply maintain its initial emptiness, it actively deepens its own hollow. The slight underdensity present in the infant universe, that faint cool spot in the cosmic microwave background, is amplified over eons into a cavernous expanse. The interior becomes increasingly depopulated, a true cosmic backwater, while the walls of the void grow sharper and more massive, accumulating the refugees from the emptiness. This is how a whisper becomes a shout. The transformation from a region that is merely less dense to one that is profoundly, overwhelmingly empty is the direct result of this great evacuation, a slow-motion sculpting of nothingness that defines the largest structures we know. The true architect of this great sorting remains unseen. For all its power, gravity needed a medium to work with, a substance that could shape the cosmos long before stars ever ignited. This is where the story of voids becomes inseparable from the story of dark matter. Those primordial seeds, the subtle hills and valleys in the infant universe, were not primarily fluctuations in the gas that would become stars and planets. They were fluctuations in the invisible, mysterious substance that makes up the vast majority of all matter, dark matter. Think of it this way: the cosmic web we see today, traced by the glittering lights of galaxies, is merely a tracing paper overlay on a much larger, invisible blueprint. That blueprint was drawn in dark matter. Its gravitational pull is the fundamental force that dictated where everything would eventually flow. In the overdense regions, dark matter collapsed first, forming vast, invisible halos. These halos then acted as gravitational wells, pulling in the ordinary gas, the baryonic matter, which cooled, condensed, and eventually formed the galaxies we can see. The story in the underdense regions is the mirror image. Here, the dark matter was spread incredibly thin from the very beginning. There were no massive dark matter halos to anchor a galaxy. Instead, the weak gravitational potential of the void meant that any ordinary matter that wandered in found no reason to stay. It was tugged away by the stronger pull of the dark matter-rich walls surrounding the emptiness. So a void is not a complete absence of dark matter, but its landscape is one of profound scarcity. The few isolated galaxies that do exist within a void are like solitary trees in a vast, rolling plain, each sitting in its own tiny, undernourished dark matter halo. This sparse population is what defines a void's gravitational character. It creates a landscape that actively repels further growth, a self-reinforcing emptiness. The dark matter scaffold, by being absent, carved out the rooms of the cosmic mansion, while the bright matter simply decorated the walls it was given. For centuries, our maps of the cosmos were flat and bright. Astronomers charted the positions of stars and nebulae, then galaxies, plotting them like cities on a two-dimensional map of the night sky. But a map of city lights tells you nothing about the shape of the continent, the depth of the valleys, or the breadth of the deserts between them. To see the voids, we needed a new kind of vision, a way to perceive the universe in its full three-dimensional depth. This required more than just knowing where a galaxy was on the sky. We needed to know how far away it was. That critical third dimension, distance, came from a phenomenon called redshift. As the universe expands, the light from distant galaxies is stretched, shifting its color toward the red end of the spectrum. By measuring this redshift, astronomers can calculate a galaxy's distance. It is like giving each point of light on our flat map an altitude, turning a sketch into a topographic model. This technique began to revolutionize cosmology in the late 20th century, but it was a monumental, systematic effort that truly unveiled the architecture of nothing. Enter the Sloan Digital Sky Survey. Beginning in the year 2000, this ambitious project used a dedicated telescope to methodically scan vast swaths of the heavens, not just taking pictures, but capturing the spectra of millions of galaxies to measure their redshifts. It was building a three-dimensional atlas of the nearby universe, painstakingly, point by point. When scientists began to plot the data, the result was breathtaking. Instead of a random scatter of lights, a vast, coherent structure emerged. Galaxies were arranged in immense, interconnected filaments and dense knots, but between these luminous structures were enormous, spherical regions of startling emptiness. The universe was not a uniform scatter of stars, it was a foam, a sponge, a cosmic honeycomb of bubbles. The Sloan map made the voids undeniable. They were not just gaps in our data, they were real, bounded volumes, some large enough to contain thousands of Milky Ways end to end with room to spare. This was the pivotal shift in perspective. Astronomy stopped being just the study of luminous objects and began the study of the luminous objects in relation to the profound emptiness that surrounds and defines them. With this three-dimensional map in hand, scientists could finally move from simply noticing the voids to formally studying them. They developed statistical tools to define a void's boundaries, to measure its volume, and to catalog its properties. What makes one void different from another? How does the density of galaxies inside compare to the walls? How spherical or elongated is it? These questions turned voids from cosmic curiosities into quantifiable, testable objects. They became laboratories. This three-dimensional map revealed a cosmic competition, a race for dominance that has been running for billions of years. On one side, the great clusters and superclusters. These are the dense intersections where multiple filaments of the cosmic web meet, the grand metropolitan hubs of the universe. Their growth is a story of accretion, of gravitational conquest. A massive cluster sits at a crossroads, and its immense gravity pulls in entire galaxies and smaller groups along the filaments that feed it, like rivers flowing into a vast lake. It grows richer and denser, a towering peak in the landscape of matter, but on the other side are the voids, and their growth follows a completely different, almost opposite set of rules. A void does not grow by pulling things in, it grows by pushing things out and by merging with its neighbors. Picture two enormous, expanding bubbles floating side by side. The thin wall of soap film between them is under tension from both sides. Eventually, that thin wall becomes unstable and ruptures, and the two bubbles merge into one single, even larger bubble. This is precisely how cosmic voids evolve. The sparse, weak walls of dark matter and galaxies that separate two adjacent voids are under constant gravitational pressure. The emptiness on either side is expanding faster than the universe itself, stretching these walls ever thinner. Finally, the wall collapses and two voids become one. It is a process of consolidation, where smaller voids merge to form the titanic structures we observe today, like vast watersheds combining into a single continental basin. This highlights a fundamental asymmetry in the cosmic architecture. While galaxy clusters are undoubtedly impressive in their density and brilliance, they are the peaks. Voids are the continents. In terms of sheer volume, voids utterly dominate the cosmos. If you could take a random cubic chunk of the universe 100 million light-years on a side, you are vastly more likely to be placing it in the middle of a void than in the heart of a supercluster. They are the default state of our universe's geography, And here is the critical twist that ensures voids will win the long-term race. Their growth is not just powered by gravity's evacuation and mergers, it is supercharged by the accelerating expansion of the universe itself. As space stretches, the distances between the already isolated galaxies inside a void increase even more dramatically. The void's interior becomes even emptier faster. Meanwhile, the cosmic expansion also helps to stretch and weaken the walls between voids, making mergers more frequent. While a galaxy cluster's growth is a local, gravitational struggle, a void's expansion is a global phenomenon, riding the very fabric of spacetime outward. They are the fastest-growing structures in the universe, their dominion of emptiness increasing with every passing moment. So we are left with a profound new perspective. The story of cosmic structure is not solely about where matter collects, but about where it has fled. The future belongs not to the brilliant cities, but to the growing silence between them. Within this growing dominion of emptiness, a few lonely lights still shine. These are the void galaxies, the cosmic hermits who did not or could not join the great migration to the walls. They are the exceptions that prove the rule, and by studying their quiet, isolated lives, we gain a unique window into how a galaxy's environment shapes its destiny. While their cousins in the dense clusters and bustling filaments are often grand spirals or giant ellipticals, brimming with activity, void galaxies tell a different story. They are frequently smaller, irregular in shape, and strangely quiet. Many astronomers describe them with terms like red and dead or anemic. This means they have largely stopped forming new stars. Their stellar populations are aging, with fewer of the brilliant, hot blue stars that signal vigorous star birth, leaving them with a cooler, redder glow. This is a direct consequence of their profound isolation. In the denser regions of the cosmic web, galaxies are constantly being fed. Rivers of fresh, cold hydrogen gas flow along the dark matter filaments, providing a continuous fuel supply for new generations of stars. A galaxy in a cluster or a filament is like a city built at the confluence of major rivers, with resources flowing in constantly. But a void galaxy is a remote outpost in a vast desert. It has been cut off from these cosmic supply lines for billions of years. It must survive on its own internal reserves of gas, and once that fuel is exhausted, star formation sputters and dies. The galaxy enters a long, quiet retirement. This environmental effect is stark. Two galaxies born with identical masses and compositions will evolve down radically different paths depending solely on their address in the cosmic web. One, nurtured in a dense filament, may become a magnificent spiral. The other, stranded in a void, may become a faded, irregular relic. These lonely galaxies are more than just curiosities, they are crucial scientific tools. By cataloging their properties, their shapes, their colors, and their gas content, astronomers can test our models of how voids actually work. Do the galaxies we find inside voids match what our theories of void evacuation predict? Their very existence and their specific characteristics serve as a fingerprint of the gravitational and evolutionary history of the void itself. They are natural probes telling us how empty a void truly is and for how long that emptiness has been deepening. In their quiet, reddened light, we read the history of the growing nothing that surrounds them. But the profound emptiness of these spaces offers more than just a record of the past. It creates a unique, almost pristine laboratory for testing the very laws that govern the cosmos. In the dense, crowded environment of a galaxy cluster, gravity's signal is a deafening roar. The immense mass of thousands of galaxies, coupled with vast clouds of hot gas and enormous halos of dark matter, creates a fantastically complex gravitational landscape. Studying the fundamental expansion of the universe in such a place is like trying to measure the gentle slope of a hillside from inside a raging tornado. The local distortions are simply too great. A cosmic void, by beautiful contrast, is a place of exceptional quiet. With so few galaxies and so little concentrated mass, the interior of a large void is the closest thing we have to a patch of smooth, average universe. The cacophony of local gravitational forces is reduced to a faint whisper. This clarity is what makes voids such powerful tools. Here, scientists can attempt to measure the pure, background expansion of space itself with minimal interference. And it is within this quiet expansion that we might detect the fingerprints of our universe's most mysterious component, dark energy. This is the hypothesized force driving the accelerated expansion of the cosmos. Its effect is subtle, a gentle pressure that acts against gravity on the largest scales. In a crowded cluster, this subtle push is utterly lost in the gravitational noise. But in the serene emptiness of a void, where the gravitational pull is already weak, the subtle repulsive push of dark energy could, in theory, leave a more detectable mark. Astronomers look for this by studying how voids themselves expand. Do they grow at precisely the rate predicted by our standard models of gravity and cosmology, or is there a slight deviation? That deviation could be the signal we need. Furthermore, the clean environment of a void is the perfect testing ground for alternative theories of gravity itself. Some physicists propose that what we call dark energy is not a separate force, but a sign that our understanding of gravity, Einstein's theory of general relativity, needs modification on cosmic scales. These modified gravity theories make specific predictions about how structures like voids should form and evolve. By meticulously mapping the shapes, sizes, and growth rates of thousands of voids and comparing them to these predictions, we can perform a grand experiment. The voids become a natural, universe-scale particle accelerator, but one that tests the fabric of spacetime instead of smashing subatomic particles. Every faint galaxy on a void's distant wall, every precise measurement of its redshift, is a data point in this experiment. In their growing silence, these vast nothings may hold the key to understanding everything. This serene emptiness leaves a mark on the oldest light in the universe. As the cosmic microwave background radiation, that ancient afterglow from the Big Bang, travels across billions of light years to reach us, it does not pass through empty, static space. It journeys through a dynamic landscape of growing voids and evolving clusters, and this journey imprints a subtle signature upon it. This phenomenon is known as the Integrated Sachs-Wolfe effect. To understand it, picture a photon, a particle of that primordial light, beginning its long voyage toward Earth. As it moves through the cosmos, it must navigate the gravitational hills and valleys created by the distribution of matter. If it flies into a gravitational valley, like the potential well of a massive galaxy cluster, it must climb out. Climbing a gravitational hill costs the photon energy, stretching its wavelength and making it appear slightly cooler or redder when we finally observe it. Conversely, if it falls into a valley, it gains energy, appearing slightly warmer. In a universe that is not expanding, these gains and losses would perfectly cancel out over the photon's entire journey. But our universe is not static, it is accelerating. The gravitational landscapes themselves are changing over cosmic time because of dark energy. This is where the profound emptiness of voids becomes crucial. A large, mature void is not just a place where matter is absent. It is a region where the gravitational potential is actually shallower than the cosmic average. It is like a gentle, broad hill of negative gravity. As a CMB photon enters this region, it actually gains a little energy rolling down into this shallow hill. But here is the critical part, because dark energy is causing the void to grow and deepen over time. The hill is actually getting shallower as the photon passes through. So when the photon climbs back out, it does not lose all the energy it gained. It emerges with a tiny bit of extra energy, appearing as a faint, warm spot on the CMB map relative to its surroundings. For a cluster, the opposite happens. The deepening gravitational well creates a subtle cold spot. This is the direct, observational fingerprint of dark energy's influence on the largest structures. The cold imprints from clusters and the warm imprints from voids in the CMB are not random noise. They align with the vast structures we have mapped in the nearby universe. This correlation is one of the strongest pieces of evidence we have that dark energy is real and that it is actively reshaping the cosmic web, causing the gravitational potentials of both clusters and voids to decay over time. The silent growth of nothingness is literally writing its signature across the sky, etched into the first light of creation. The warm and cold imprints left on the cosmic microwave background are not the only ancient echoes we can use. There is another, even more precise fossil from the universe's infancy, one that acts as a cosmic yardstick embedded in the very distribution of galaxies. This fossil is known as Baryon acoustic oscillations. In the first few 100,000 years, the cosmos was a seething, opaque plasma, a fluid of light and matter. In this dense soup, gravity tried to pull matter together into clumps, but the intense pressure of the trapped radiation created powerful sound waves that pushed back. These waves rippled outward from every slight overdensity, like a stone dropped in a pond, but they could only travel so far before the universe cooled enough for atoms to form. At that moment, about 380,000 years after the Big Bang, the waves froze in place, leaving a distinct spherical shell of matter at a very specific distance from each seed. This characteristic scale, the distance those sound waves traveled, is our standard ruler. It is about 500 million light-years across today. When we look at maps of the universe, we see a subtle statistical preference for galaxies to be separated by this exact scale, a faint echo of those primordial sound waves. Traditionally, scientists measure this BAO signal by looking at the clustering of all galaxies, but there is a problem. The dense, chaotic environments of clusters and superclusters can distort this delicate signal, like trying to hear a faint, pure tone in the middle of a roaring city. This is where the serene architecture of voids offers a brilliant solution. Instead of using all the bright, noisy galaxies, astronomers can use the geometry of the emptiness itself. They look at the distance from the precise center of a void to the surrounding wall of galaxies that defines its boundary. Because voids are such clean, symmetric structures, these walls tend to form at a very specific distance related to that primordial sound wave. The void center acts as a stable, geometric reference point, the equivalent of the center of the ripple, and the wall is the fossilized shell. By stacking the measurements from thousands of voids, scientists can measure the BAO scale with exceptional precision. This method is cleaner because the void environment is simpler, less disturbed by the later, messy effects of galaxy formation and violent mergers. It is like moving our listening experiment from the noisy city center out to a quiet desert, where the faint echo can be heard with perfect clarity. Each void in a catalog becomes a single, exquisite measurement of the universe's ancient heartbeat. By comparing the apparent size of this standard ruler at different distances, and thus different eras in cosmic history, we can chart exactly how the expansion of the universe has changed over time. This gives us our most stringent constraints on the nature and strength of dark energy, the force that now governs the fate of all structure. In the profound quiet of these growing nothings, we find the clearest echo of the universe's first sound, a ruler etched in emptiness to measure the acceleration of everything. This precise cosmic yardstick has revealed a crack in our understanding of the universe's expansion. Astronomers call it the Hubble tension, and it is one of the most significant puzzles in modern cosmology. Simply put, we have two primary ways to measure how fast the universe is expanding right now, a value known as the Hubble constant. One method looks locally, using nearby stars and galaxies as mileposts. The other method looks back to the early universe, using the cosmic microwave background and the Baryon acoustic oscillations we just discussed as a pristine, ancient ruler. These two methods, performed with incredible precision, give different answers. The local universe appears to be expanding faster than the early universe data predicts it should be. The discrepancy is not large, but it is stubborn and persistent, suggesting we may be missing a fundamental piece of our cosmic model. Could the answer lie not in the laws of physics themselves, but in our place within the cosmic architecture? This is where the story of voids takes a startlingly personal turn. What if our entire local group of galaxies, and the wider region we survey for our local measurements, is not in an average part of the cosmos? What if we reside inside a local underdensity, a vast but subtle void of our own? It is a compelling hypothesis. If we are sitting in a region of space that is less dense than the cosmic average, the local gravitational landscape would be unusual. Remember, gravity from surrounding matter slows the expansion of space. In a region with less matter, there is less gravitational braking. Therefore, space within our local void would be expanding slightly faster than the true global average. Our local measurements using supernova and other nearby objects would then be measuring this faster local rate. Meanwhile, the early universe measurements from the CMB and BOS probe the entire, smooth cosmos and give us the true global average expansion rate. The tension, then, would not be an error but a cosmic illusion created by our address. We would be like sailors in a calm lagoon, measuring the local tides, unaware that the global ocean has a different rhythm entirely. The idea is elegant, but the debate is fierce. To resolve the Hubble tension, this local void would need to be immense, perhaps 600 million light-years across or more, and significantly underdense. Some large-scale surveys have found hints of such a structure, a vast region sometimes called the KBC void or the local hole, where galaxy counts are lower than expected. Other analyses, however, suggest the evidence is not strong enough, that our local neighborhood is fairly typical after all. The scientific conversation is ongoing, a rigorous back and forth of data analysis and statistical interpretation. This debate itself is a testament to how profoundly our view of the cosmos has shifted. We are no longer just mapping where things are. We are critically questioning how our own position within the grand tapestry might skew our perception of reality. Whether or not a local void ultimately explains the Hubble tension, the investigation forces us to confront a humbling possibility. Our most precise measurements of the universe's fate might be filtered through the quiet emptiness of our own cosmic backyard. The possibility that our cosmic address is special forces a profound question. How can we trust any of our grand theories about voids, dark energy, or the entire cosmic web? The answer lies not in more observation alone, but in the power to create entire universes inside supercomputers. To truly understand how cosmic voids became the largest structures, we must build them ourselves from the ground up. This is the realm of cosmological simulations, where we write the laws of physics into code and set them in motion, watching to see if a virtual cosmos grows to look anything like our own. The challenge is staggering. You begin with a digital box representing a chunk of space-time, and you fill it with particles. These are not particles of matter in the traditional sense, but tracers that represent packages of dark matter and ordinary gas. You seed this box with the exact same pattern of microscopic fluctuations we see in the cosmic microwave background, the primordial hills and valleys. Then you press play. The simulation must calculate the gravitational pull between every single one of these millions, or even billions of particles, as they move through an expanding universe. It is a dance of unimaginable complexity, tracking how these particles clump, stream, and evacuate over billions of virtual years. The most advanced simulations, with names like IllustrisTNG, Eagle, or Uchuu, do not stop with gravity and dark matter. They incorporate the messy, complicated physics of the ordinary stuff, the baryons. This means simulating how gas cools, collapses, forms stars, and how those stars then explode, blowing material back out into space, enriching it with heavy elements. These supernova explosions can generate powerful winds that push gas out of small galaxies, affecting the very environment of a growing void. Getting this right is crucial, because the galaxies we see are our only observational handle on the invisible dark matter scaffold. The ultimate test is both simple and profound. When the simulation reaches the present day, when the virtual clock ticks 13.8 billion years, we stop and look. Does the resulting cosmic web resemble the one mapped by the Sloan Digital Sky Survey? More specifically, does the population of voids match reality? Do we see the same distribution of sizes, from small pockets to titanic bubbles? Are the void walls sharp and defined? Are the galaxies inside those voids the right kind, older and quieter? When the simulated universe passes these tests, it is a moment of extraordinary validation. It means our understanding of the initial conditions of gravity, dark matter, and galaxy formation is fundamentally sound. The voids that emerge are not programmed in, they are a prediction, a natural consequence of the rules we wrote. Their existence and properties in the simulation confirm that we have captured the essential story of cosmic evolution. Yet even the most successful simulations leave mysteries on the table. They show us the how, but they also highlight lingering questions about the why. Even the most successful simulations reveal a cosmos that refuses to be neatly labeled. As astronomers began cataloging these immense bubbles of nothing, a simple question emerged. What exactly counts as a void? The answer is surprisingly complex, leading to a whole science of classification, a taxonomy of emptiness. It turns out not all voids are created equal. Their character is deeply shaped by their cosmic neighborhood, a distinction captured by two evocative terms, void in cloud and void in cloud. A void in cloud is exactly what it sounds like, an empty region embedded within a larger, diffuse, lower-density environment. It is like a small air pocket inside a larger, softer sponge. These voids tend to be smaller and are often found nestled within the broader, emptier regions of the cosmic web. Their evolution is more isolated. In contrast, a void in cloud is far more dramatic. This is a void that has managed to form and expand within a globally denser environment, like a giant bubble blown into a thick gel. These voids are rarer, but they are the titans. Because they are surrounded by denser material, the gravitational contrast at their boundaries is extreme. The walls are sharper, the evacuation more complete, and their growth, fighting against a stronger gravitational pull from their surroundings, is a testament to the powerful outward pressure of the void's own underdensity. They are the most pristine and emptiest voids we can find. This classification matters because a void's environment dictates its entire life story, from its initial formation to its ultimate fate, shaping everything from the types of galaxies left inside to how it will merge with its neighbors. Beyond this binary, cosmologists see an intricate hierarchy. The cosmic web is not made of simple, isolated bubbles. Look closely at a large void, and within its expansive interior, you will often find smaller, secondary voids. These are sub-voids nestled inside the larger parent like hollows within a vast cave system. This recursive structure, voids within voids, is a direct prediction of how the initial random fluctuations evolved. The largest underdensities contained smaller ones, and as gravity evacuated the big void, it also amplified these smaller interior pockets. This hierarchy is a fractal signature, a reminder that the architecture of nothing has its own rich, layered complexity. So how do we actually find and measure these ephemeral structures in the vast datasets of galaxy surveys? There is no single, perfect tool. Different research groups use different algorithms, each with its own philosophy, much like using different nets to catch different types of fish. One popular method is the watershed algorithm. Imagine taking a three-dimensional map of galaxy densities and inverting it so the dense clusters become deep valleys and the empty voids become high peaks. Then simulate a universal rainfall over this inverted landscape. The water will flow downhill, collecting into basins. Each distinct basin defines a void, with its watershed ridge marking the boundary where water would flow into a different basin. This method is excellent for finding the overall topology of the web, capturing the interconnected, sponge-like nature of the voids. Another common approach is the spherical underdensity method. This algorithm starts by placing random spheres in the galaxy map and then grows them until the average density of galaxies inside the sphere reaches a certain, very low threshold. The resulting sphere defines a void. This method tends to find more spherical, isolated voids and is very useful for creating clean, uniform catalogs for statistical studies. The fact that there is no single agreed-upon definition is not a flaw in the science, but a reflection of reality itself. Voids do not have sharp, solid edges like a soap bubble. Their boundaries are fuzzy, transitional zones where the density smoothly increases from the profound emptiness of the interior to the richer walls of galaxies. One algorithm might draw the boundary here, another might draw it there. This inherent fuzziness is a fundamental feature of these structures, born from the gentle, statistical nature of the initial seeds and the smooth action of gravity. The quest to classify the emptiness, therefore, is not about imposing a rigid order on the cosmos. It is about developing a shared language to describe the nuanced, hierarchical, and beautifully ambiguous architecture of the growing nothing. The ultimate fate of these titanic structures is written into the accelerating fabric of space itself. As we project the cosmic clock forward, the quiet growth we observe today becomes a runaway expansion, a future where emptiness is the only victor. The driving force is dark energy, that mysterious pressure inherent to space. While its effect is subtle now, its influence is cumulative and relentless. As the universe continues to expand, dark energy becomes increasingly dominant because its density remains constant while the density of matter thins out. Think of it as a gentle but unceasing tailwind that gradually strengthens as the cosmic landscape opens up. This acceleration does not just affect the space between galaxies, it fundamentally reshapes the architecture of the cosmic web. Voids, already the fastest-growing structures, will experience a profound turbocharge. Their interiors, already sparse, will stretch at an ever-increasing rate. The few remaining galaxies inside a void will find themselves pulled apart, their distances growing so vast that they would vanish from each other's skies even if they lasted forever. But the real transformation happens at the boundaries. The accelerating expansion actively weakens the gravitational glue holding the walls and filaments together. Those thin sheets of galaxies defining a void's edge are under constant tension, pulled inward by their own gravity but stretched outward by the expanding space within the void. As dark energy's push grows stronger, it will eventually overcome gravity's pull on these large, diffuse structures. The walls will stretch thin and finally fragment. When this happens, two adjacent voids will merge. This process will cascade across the cosmos. The sponge-like structure will coarsen. Smaller voids will combine into colossal supervoids, regions of emptiness spanning billions of light years. The cosmic web, that beautiful, intricate network of filaments, will be pulled apart. The dense knots of superclusters will remain as isolated islands, but the threads connecting them will stretch and snap. A galaxy in a filament will look out and see the other bright knots of its chain receding into darkness, their connections severed by the growing emptiness. The universe of the far future will be a stark and lonely place. Countless galaxies will remain, but they will be imprisoned within their own gravitationally bound clusters. floating like isolated archipelagos in an ever-darkening, ever-widening ocean of nothing. The background sky beyond the local group will fade to perfect black as the light from distant structures red shifts beyond detection. In this final act, the voids achieve total dominion. The story that began with microscopic whispers of underdensity concludes with these whispers having expanded into a cosmic shout that fills all of reality. The architecture of matter dissolves, leaving behind only the enduring, accelerating architecture of emptiness. This stark future is not our destination, but a distant horizon. Our present is one of discovery, where new eyes are about to open on the cosmos, transforming these voids from mapped structures into instruments of exquisite precision. The next leap in understanding will come from a new generation of observatories, projects so vast in scope they will redefine our atlas of emptiness. Leading this charge is the Vera C. Rubin Observatory and its decade-long legacy survey of space and time. Perched atop a mountain in Chile, its immense mirror and gargantuan camera will scan the entire southern sky every few nights, not once but over and over for 10 years. It will not just take pictures, it will make a movie of the universe. This relentless observation will detect billions of galaxies, measuring their shapes and positions with staggering detail. For the study of voids, this is a revolution in data. The Rubin LSST will not simply find more voids, it will map their evolution in time. Astronomers will watch as voids subtly change shape and size over cosmic epochs, tracing how dark energy influences their growth with a clarity we have never possessed. It will see the faint, distorted shapes of galaxies behind voids, using the emptiness itself as a gravitational lens to weigh the sparse dark matter within. Simultaneously, soaring above Earth's atmosphere, the European Space Agency's Euclid spacecraft is conducting its own monumental survey. Euclid's specialty is exquisitely precise shape measurement. It will observe billions of galaxies to trace the subtle distortions caused by the dark matter web, a technique called weak gravitational lensing. When applied to voids, this is like giving us an MRI scan of the cosmic skeleton. Euclid will measure the precise density profile of a void's walls and interior, telling us exactly how matter is distributed from the profound emptiness at the center to the dense ridges at the edge. This data will test our theories of gravity with unprecedented rigor. Do the shapes and growth of these voids match the predictions of Einstein's relativity, or do they hint at something new? Together, these missions represent a shift from cataloging voids to using them as calibrated probes. Each precisely mapped void becomes a single data point in a grand experiment. By combining millions of them, we will have a statistical power that can detect deviations from our standard models that are smaller than 1%. We are on the verge of turning the largest nothings in the universe into our most sensitive instruments for listening to the whispers of new physics. This quest to use emptiness as an instrument leads us to a profound crossroads in physics. The standard model of cosmology, known as lambda CDM, is brilliantly successful, but it rests on two profound unknowns, dark matter and dark energy. For some scientists, the serene environment of a cosmic void is the perfect place to ask if we have been describing the cosmos with the right rulebook. Could the phenomena we attribute to invisible substances actually be a sign that our understanding of gravity itself is incomplete? This is not a fringe idea, but a serious line of inquiry that uses the largest structures in the universe as its laboratory. In our standard model, gravity follows Einstein's theory of general relativity everywhere. The strange motions of galaxies and the accelerating expansion are explained by adding dark matter and dark energy to the cosmic inventory. But alternative theories propose a different path. They suggest that gravity does not weaken with distance exactly as Newton and Einstein predicted, especially in regions of extremely weak gravitational fields. One prominent class of these ideas is called modified Newtonian dynamics, or MOND. In such a framework, the very low density inside a cosmic void creates a unique gravitational environment. Without the overwhelming pull of concentrated mass, any subtle deviation from Einstein's rules should become magnified, like hearing a faint off note in a silent room. These theories make specific, testable predictions about how voids should behave. For instance, how quickly should a void's walls expand outward? How should the sparse galaxies within a void move relative to one another? What precise shape should a mature void take? And how does that shape relate to the density of its surroundings? In general relativity with dark energy, the answers are one set of numbers. In a modified gravity theory, they are often a different set. This is where the new data from observatories like Vera C. Rubin and Euclid becomes revolutionary. They are not just mapping voids, they are measuring these properties with exquisite precision, turning each void into a calibrated gauge. Scientists will compare the real, observed void shapes and growth rates against the predictions of both the standard model and its alternatives. It is a direct observational showdown. If every measured void aligns perfectly with the lambda CDM predictions, it strengthens the case for dark matter and dark energy as real components of the universe. But if the data consistently shows a slight skew, a subtle mismatch in how these vast bubbles evolve, it could be the first hard evidence that gravity itself needs a rewrite on cosmic scales. The growing silence of the voids may soon tell us if we have been missing invisible actors, or if we have been misreading the lines of the fundamental force that holds the script of the cosmos together. The quiet growth of these vast nothings carries a profound weight, a philosophical shift in how we see our place in the cosmos. For centuries, the human story has been one of centrality, a belief that the universe was built around places like ours, teeming with matter and light. Cosmic voids dismantle that assumption with silent, overwhelming scale. They force a humbling realization. The most common, default volume of space in our universe is not a star-filled galaxy or a bustling cluster. It is a profound and enduring emptiness, a realm where conditions for life as we know it are not just absent but impossible. These are not barren wastelands waiting to be filled, they are the dominant reality. Our vibrant, complex corner of existence is the rare exception, a fleeting spark in an ocean of dark. This challenges a deeply ingrained perspective, the idea that the cosmos is inherently built for us, or that our presence is its natural outcome. Instead, we find ourselves clinging to a dense filament, a thin wall in the cosmic sponge, surrounded by a growing dominion of void. Our existence is not the point of the structure, but a beautiful, incidental feature of its architecture. This realization is not a message of despair, but of awe. It reframes the cosmic narrative. Emptiness is not a failure of structure, a cosmic mistake where matter failed to collect. It is the necessary and direct counterpart to the dense knots and filaments. Both are children of the same primordial seeds and the same universal laws. The gravitational physics that patiently gathered hydrogen into stars and planets in overdense regions is the exact same force that ruthlessly evacuated the underdense regions, creating these titanic bubbles. The void and the galaxy are two sides of the same coin, forged in the same furnace. One cannot exist without the other. The cosmic web is a balanced whole, a single expression of the universe's evolution. In this light, our own story gains a deeper resonance. We are not separate from the emptiness, we are shaped by it. The very laws that carved these vast hollows also, in their other manifestation, carved the conditions for our solar system. We are a product of the same grand tension that defines all structure. To understand the cosmos, then, we must learn to value the silence as much as the song. The growing voids are not just astronomical objects, they are a fundamental part of the universe's character, a necessary canvas of absence that gives meaning to every point of light. Among the countless bubbles of emptiness, one stands out as a legend. The Boötes Void, sometimes called the Great Nothing, is a staggering example of just how profound cosmic emptiness can become. Its story began in the early 1980s when astronomers Robert Kirshner and his colleagues were conducting a redshift survey, mapping galaxy distances in the constellation of Boötes. As they plotted their points, they stumbled upon a spherical region of the sky where the galaxies simply vanished. It was a hole in the universe, a void of such scale and purity that it redefined what was possible. Modern measurements show it spans roughly 330 million light-years in diameter. To grasp that scale, if you placed our Milky Way at one edge, even traveling at the speed of light, it would take you over 300 million years to reach the other side, and you would encounter almost nothing along the journey. Within that colossal volume, you would expect to find thousands of galaxies based on the cosmic average. Instead, surveys have confirmed only about 60. The space is so empty that if the Milky Way were located at its center, we would not have known other galaxies existed until the 1960s. The few galaxies that do call this void home are peculiar. They are often isolated, irregular in shape, and show signs of a quiet, aging stellar population. They are cosmic castaways, islands of star formation cut off from the nourishing flows of intergalactic gas that fuel their cousins in denser regions. Their very existence and their strange properties serve as a perfect natural laboratory, confirming our theories about how a galaxy's environment dictates its fate. The Boötes Void is not just an empty space, it is a monument to the power of gravitational evacuation, a place where the process of void deepening has operated with breathtaking efficiency. But such an extreme object raises a critical question. Is the Great Nothing a bizarre statistical fluke, a 1 in a trillion accident in the distribution of matter, or is it something our cosmic models actually predict? The answer lies in the nature of the initial seeds from which all structure grew. Our best simulations of the cosmos, which start with the tiny fluctuations seen in the cosmic microwave background and let gravity run its course, do indeed produce a few voids of comparable scale. They are rare, but they are not impossible. In a universe born from random quantum whispers, you expect a statistical distribution, a cosmic bell curve. Most voids will be of moderate size, but the curve has a tail. Every so often, by chance, several smaller underdensities will merge and align in just the right way to produce a supervoid, a titan of emptiness like the one in Boötes. Its existence, therefore, is not a crisis for cosmology, but a validation. It tells us that our understanding of the initial conditions and the growth of structure is fundamentally correct, capable of predicting even the most extreme outliers. Yet, it also serves as a humbling reminder. The universe is under no obligation to be uniformly interesting. It can, and does, craft regions of staggering nothingness that dwarf our entire local supercluster, places where the story of cosmic evolution wrote a chapter of profound and lasting silence. The profound silence of a cosmic void stretches the imagination toward the very edges of reality itself. This contemplation leads us from the largest structures within our universe to a staggering possibility about the nature of our universe as a whole. Some of the most ambitious theories in physics propose that our entire cosmos, with all its galaxies, filaments, and titanic voids, might itself be just one bubble in a frothing, infinite sea of other universes. This is the speculative frontier of the multiverse, and the story of cosmic voids provides a hauntingly familiar analogy. The leading theory for how such a multiverse could arise is called eternal inflation. It suggests that in the first fraction of a second after the Big Bang, the fabric of spacetime underwent a period of hyper-accelerated, inflationary expansion. According to this idea, this inflation never truly stopped everywhere. Instead, it continues eternally in a background sea of hyper-expanding space. But within that raging sea, random quantum fluctuations can cause pockets of this inflating space to settle down, to decay into a more stable, calm state. Each of these pockets stops inflating and begins its own internal evolution, cooling, forming particles, galaxies, and eventually cosmic voids. Each pocket becomes a separate bubble universe with its own distinct laws of physics, utterly disconnected from all the others. Now consider the scale. In this picture, our entire observable universe, everything we can see out to the cosmic microwave background, is contained within one such bubble. The vast walls of our bubble, the boundary where our stable vacuum meets the eternally inflating sea outside, would be unimaginably far beyond our cosmic horizon, forever out of reach. And within our bubble, the largest structures are the voids. This invites a dizzying, recursive thought. Could the cosmic voids we map within our universe be faint, fractal echoes of that grander bubble structure? Are we, in mapping the sponge-like architecture of our cosmos, looking at a miniature reflection of a multiversal foam? It is a purely theoretical connection, but a compelling one. The voids we study are regions of lower density within our universe's specific vacuum state. The bubble universes in eternal inflation are regions of different vacuum state within a greater meta-reality. Both are defined by boundaries and interiors, both are born from fluctuations, and both represent a dominant volume of a particular kind of emptiness. This speculative link turns voids into more than just cosmic structures. They become conceptual bridges. Studying how voids form, evolve, and merge in our universe gives theorists a mathematical sandbox to model how bubble universes might interact in a hypothetical multiverse, if they ever could. The physics is, of course, vastly different in scale and mechanism, but the patterns of geometry and expansion share a family resemblance. This is where the science becomes a profound exercise in perspective. The same intellectual tools we use to understand the growing nothingness around us are the tools we use to ponder the possibility of everything else. While we have no empirical evidence for other universes, and may never have, the investigation itself reshapes our questions. It asks us to consider whether the great voids are not just the end result of our universe's story, but perhaps a hint of its origins in a far grander and even emptier meta-cosmic landscape. From microscopic quantum whispers to titanic realms of near-nothingness, the journey of cosmic voids is the central narrative of our universe's structure. It began with the faintest ripples in the newborn cosmos, imperfections that gravity would spend billions of years amplifying. But gravity's work was not singular, it was dual. In the hills of matter, it pulled inward to build galaxies. In the valleys of underdensity, it pushed outward, actively evacuating them, turning gentle dips into cavernous hollows. This great sorting, scaffolded by dark matter, created the cosmic web we see today, a sponge where the empty bubbles are not the background, but the dominant architecture. To understand the cosmos, then, is to understand this framework of emptiness. It is not about studying nothing, but about deciphering the vast, invisible container that holds every galaxy, every star, and every world. Within the serene quiet of these voids, we now place our most sensitive instruments. Their precise shapes and relentless growth are becoming our clearest signals, our most powerful tools for probing the universe's deepest mysteries. They are the key to measuring dark energy's subtle push, to testing the very laws of gravity, and to forecasting the ultimate fate of all structure. As these immense nothings continue their silent expansion, they carry the answers to our biggest questions within their growing boundaries. The story of the universe is, in its final chapters, the story of its voids. If you found this journey from quantum seeds to cosmic emptiness compelling, please subscribe for more deep dives into the universe's grandest mysteries.